Hello everybody, welcome to AS online platform. Here we are discussing about the power system subject for SSC JE and RRB JE. Right? So as I told you, the subject here it is the power systems, and my name is DMV Prasad Mehavarna, and I have done my MTech in 2010 and I am pursuing my PhD. Right? Now here I am here to teach you power systems. In that power systems particularly we are going to discuss about right? So power fault analysis. This is the syllabus of power systems. If you see the syllabus of power systems, it is consisting of generation of electrical energy and transmission and distribution of electrical energy, fault analysis, switchgear and protection, and utilization of electrical energy. Right? These are the major important concepts, and this is the complete syllabus content for the SSC JE and the RRB JE students. Clear? And in this class, we are going to discuss about some basic concepts about the fault analysis. Fault analysis. Right? Fault analysis is the complete analysis part of power system. And to understand fault analysis, what are the things we have to study, and how to solve the problems, and how to solve the questions, whatever they are asking in the fault analysis, we have to see clearly. Right? And coming to the syllabus of fault analysis, right? Before that, so coming to the textbooks, whatever you are going to prefer, right? So these are the textbooks we can prefer for fault analysis. So one is Power System Analysis by Stevenson, and Power Systems by John Wheely Publications, and Duncan Glover, Power System Analysis and Design, and Modern Power System Analysis by the best authors of India, D.P. Kothari and Eisenagrat. And along with that, so we can prefer this textbook for utilization of electrical energy, generation and utilization of electrical energy by Sivanagaraju. And this textbook we can prefer, right? So J.B. Gupta is a textbook we can prefer for some objective questions, and C.L. Wadhwa we can prefer. And these are the textbooks which are consisting of some objective questions, right? So these three textbooks are consisting of some objective questions at the end of each topic, so that you can practice them. Clear? And whereas these textbooks 1, 2, 3, 4, those textbooks are preferred only for learning the power system subject, right? And for higher standard exams like engineering services or the GATE, so we can prefer these 4 textbooks. But whereas for SSC JE and RRB JE, right? So we can prefer these textbooks, and we can practice some concepts, some questions at the end of these textbooks. Clear? Right. And next one, so we are going to see the fault analysis. So in this fault analysis, right? So these are the concepts we are having. See here, to understand the fault analysis, so first of all we have to go for the per unit system representation of the entire power system. The per unit system representation of the entire power system is nothing but, so actually we are having some problems in the absolute system. To avoid those problems, we are going for the per unit system analysis. So the absolute system is measuring the voltage in volts, current in amperes, power in different units. So active power, reactive power, apparent power, we are having different units. But whereas coming to the per unit system, we are not having any units, so that the complexity of calculations will be reduced. So to reduce the complexity in the calculations and to solve the largest power system network, very simply we are going for the per unit system analysis. And later on we are going for analysis of unbalanced system by using the symmetrical components, right? So fault analysis, in the sense we are completely analyzing the unbalanced system, right? So you can simply say this analysis is the unbalanced system analysis. Unbalanced system analysis. Right? Now, to analyze the unbalanced system, we are going to study about the symmetrical components, and later on symmetrical networks of the entire power system. So all power system elements, what are the power system elements we are having? Generators, transformers, transmission lines, and loads, right? For all those elements, we are going to construct the networks. And later on, we will see the fault analysis. So this is the syllabus point you are having in your syllabus. But to understand the fault analysis, these are the remaining chapters you can understand. Clear everybody? So here directly you cannot go directly into the fault analysis. First of all, you have to learn per unit system analysis. Later on, symmetrical component theory and construction of symmetrical networks for various power system elements we have to see. And finally, we have to go for the fault analysis. Clear, students? Now, see here, coming to the just starting point of the fault analysis, we have to see what are the different types of faults in the system. Majorly, there are two types of faults. One will be because of the open circuits and one will be because of the short circuits. Open circuit faults are nothing but open conductor faults or series faults. And the second one is the short circuit faults are nothing but the shunt faults. See here, series faults are the open conductor faults or open circuit faults, and shunt faults are nothing but short circuit faults. Short circuit faults. Now we'll see individually about series faults and shunt faults clearly. See here, first of all, if you see the open circuit faults, the first one is one conductor open fault. The first one is one conductor open fault. So whenever you are having A, B, C phase sequence, in A, B, C phase sequence, when one conductor got opened, that is one conductor open fault. And here remaining two phases are safe. And second one is two conductors open fault. In case of two conductors, so A phase and B phase are open and C phase will be under safe condition. Clear? So here the current flowing in this portion will become 0, and here it is not equivalent to 0, and here it is also not is equivalent to 0, right? So here it will be 0, and here it is not 0, and here it is also not 0. The current will be existed in B phase and C phase. And whereas here the current flowing here it will be 0, and the current flowing here it will be 0, and the current flowing here it is not will be 0. That is the two conductors open fault. And whereas in case of three conductors open, here the current will be 0, and here the current will be 0, and whereas here the current will also be 0. In all the three cases the current will be 0, so that we cannot consider this as a fault. We cannot consider this as a fault. So it is a open circuit condition. Open circuit condition or no load condition, simply you can say, or no load condition. Clear, everybody? So that we can consider only one conductor open fault and two conductors open fault as the fault, and you cannot consider three conductors open fault as the fault. You can consider three conductors open fault as the no load condition of the system. So these are the various types of open conductor faults or open circuit faults. And coming to the short circuit faults, the various types of the short circuit faults. So here first one is line to ground fault. Line to ground fault. If you check here, one line has been grounded. One line has been grounded. So actually we'll consider a system. So this is the system we are having. That is the power system network. Power system network we are having. This power system network, initially it is having three transmission lines, and it is operating under no load condition. No load condition. Under this case, the current flowing in this phase, it is IA, which is equivalent to 0. The current flowing here it is IB, which is equivalent to 0. The current flowing here it is IC, which is also equivalent to 0. So all the three currents IA, IB, IC are 0 because we are saying that it is a no load operation of the system. So under no loaded condition, whenever you are getting a fault, one line is grounded, so that it is having a path for the current flow. So that here current IA is 0, IA is 0, and here the current IB is 0, but here the current IC is not is equivalent to 0. So that fault we can call it as the line to ground fault. Line to ground fault case. Clear? And coming to the next fault, it is the line to line fault. Line to line fault. So that two phases have been short circuited. Therefore, they are allowing a current to flow in between them. They are allowing a current to flow in between them. Therefore, the current in this phase IA is equal to 0, and whereas here IB is not is equivalent to 0, and here it is also IC is not is equivalent to 0. So that under no load condition also this system is allowing the currents, so that this is the next fault, that is line to line fault. Line to line fault. So these are the two faults here. So one is line to ground fault when single line has been grounded, and this will be line to line fault whenever two lines have been short circuited. Two lines have been short circuited. And coming to the next one, it is the line to ground fault. Line to ground fault. So that in this case, the current in this phase IA is equal to 0, and here IB is not is equivalent to 0. Why? Because it is having a path to the current flow, and here it is also IC, which is not is equivalent to 0. Clear? Right. So IC is equivalent to not is equivalent to 0. So we are having IB and IC currents under no loaded condition, so that we can say there is a fault on the system. As IB and IC both are flowing to the ground, we are saying it as line to ground fault. Please check here, the fault current in the system, is flowing in this path, that is the fault current path, and whereas here the fault current path will be this one, and whereas in line to ground fault we are having the fault current in this zone. That is the line to ground fault. And coming to the three-phase fault, triple line fault. So in this case, all the currents are flowing under no loaded condition whenever the fault occurs. IA is not is equivalent to 0, and IB is not is equivalent to 0, and IC is not is equivalent to 0. So as all the faults have been involved in the fault, so we can say the sum of the currents IA plus IB plus IC is always is equivalent to 0. So as we have discussed in open circuit fault or open conductor fault, when all the three phases are open circuited, that's not a fault. That is the balanced condition of the system. We can consider that condition as the no load condition of the system. And coming to, in this case, short circuit fault also, when all the three phases if involved in the fault, the fault will be equally divided into all the three phases. Then we can say the sum of the currents IA, IB, IC, you will get it as 0. Therefore, whenever you are getting IA plus IB plus IC is equivalent to 0, IA plus IB plus IC is equivalent to 0, then we can say that is a balanced condition. Clear? So that we can say this fault as the balanced fault. And coming to the next one, it is the three-phase to ground fault. So in this case, under no loaded condition, whenever the fault occurs, the current will be flowing here. IA is not is equivalent to 0, and IB is not is equivalent to 0, and IC is not is equivalent to 0. And whereas the fault current in both the cases may be flowing in any path. It may be here or it may be here, anywhere. Here you can take here somewhere. And in this case also, the fault current may be flowing somewhere here, or it may be flowing here, or it may be flowing here also. Clear? So that is the three-phase to ground fault case. So here also all the three phases have been involved in the fault, so that the sum of the currents IA plus IB plus IC is equal to 0. So whenever you are having IA plus IB plus IC is equal to 0, then we can say what is that condition? That's a balanced condition. Clear? So that this fault is also a balanced fault. Balanced fault. So in power system terminology, we can call that fault as balanced fault or the symmetrical fault. Symmetrical fault. Now if you see, the types of faults, the types of short circuit faults. Short circuit faults. Faults. The types of the short circuit faults are, first one is line to ground fault, LG fault, simply you can call it as. Second one is line to line fault, LL fault. And third one is double line to ground fault, LLG fault, double line to ground fault. And the fourth one is triple line fault, three phase fault, line to line fault. And the fifth one is line to ground fault, three phase to ground fault. And here we are saying in these two cases, IA plus IB plus IC is equal to 0. So that this is the condition of balanced system. Balanced system. Therefore, we can call these two faults as balanced faults or the symmetrical faults. So these two are called as balanced faults or symmetrical faults. Symmetrical faults. And whereas LG, LL and LLG, in these three cases, so we cannot get IA plus IB plus IC will not be equivalent to 0. Will not be equivalent to 0. So that the system will be unbalanced. Unbalanced system. So that these faults are called as unbalanced faults or unsymmetrical faults. So these faults are called as unbalanced faults or unsymmetrical faults. Unsymmetrical faults. So that is the condition of LG, LL and LLG faults and triple L and triple LG faults. Clear? Now, in these faults, LG fault is nothing but the probability of occurrence. The probability of occurrence of LG fault will be so very high. So approximately 75% of the entire faults we can consider them as the line to ground faults. So the probability of occurrence of those faults. And triple LG fault are the least probable faults, triple L or triple LG faults. So these faults are also called as the three phase faults. Three phase faults. So the probability of occurrence of the three phase faults will be very, very less, and the probability of occurrence of LG fault will be very large. Clear? Therefore, we can say LG fault is the most common fault. LG fault is the most common fault. LG fault is the most common fault. In the system. And the severity of this fault is also very, very less compared to that of the remaining faults. We'll see in the later cases. So how LG fault is least severe and how triple L faults are most severe. So here I am writing the statement here. It is the least severe fault. Fault is the least severe fault. Least severe fault. And coming to the most severe and least common fault, right? Three-phase faults, both three-phase faults are the least common faults, least common faults. Least common faults, and they are the most severe faults. So three-phase faults are the most common faults. Sorry, most severe faults. Most severe faults. And if you particularly ask, right, so in these two, that means in triple L and triple LG faults, in triple L and triple LG faults, which is the most severe fault, means that actually triple LG fault is somewhat more severe whenever the pre-fault system is unbalanced, right? So you can make that point also. So when the pre-fault system is unbalanced, when the pre-fault system is unbalanced, then triple LG fault, right? Triple LG fault is more severe than triple L fault. Triple L fault. Clear? So actually triple LG fault is the most severe fault. Our three-phase faults are the most severe faults, and LG fault is the least severe fault. Clear, everybody? Right. Now we'll see. So what are the consequences of the short circuit faults, which is very, very important that we have to know. Right? So we'll see individually very clearly. The consequence of the short circuit faults are, first one, we are having the under voltages, over currents, low power factor operation, unbalanced operation, low frequency, and unstable operation. Unstable operation. So now we'll see this very clearly. So whenever we are having a system like this, suppose we are having a generator connected to one bus, and at the end of this one we are having one more bus, and they are connected with some transmission lines. Suppose this bus 1 and this is bus 2, and we are having one more bus here somewhere, and these are connected like this. This will be bus 3. And bus 1 voltage is V1 at an angle of delta 1, and bus 2 voltage is V2 at an angle of delta 2, and bus 3 voltage is V3 at an angle of delta 3. Therefore, whenever a fault occurs at one particular bus, the voltage at that bus will be reduced. So that we can say this is the low voltage operation. So that we can get low voltage at that particular bus. So whenever a fault occurs, suppose it is the short circuit fault we are discussing, right? So whenever you are having the short circuit fault at that particular bus, whenever it is grounded, the ground potential will be 0 volts, so that it is trying to make that bus voltage also 0 volts. Because of that one, we can get the low voltage operation at that particular bus. Clear? Right. And along with this one, if you take a simple system like this, very simple system, generator, line, and the load. This is the load we are having. And this is the line. The line impedance is Z line, and the load impedance is Z load. The current flowing in the system is I in this direction. The bus 1 voltage is V1 and bus 2 voltage is V2. So let it is the reference at an angle of 0, and it is the non-reference at an angle of delta. Now in this equation, whenever you are having a fault, at this bus, So that what happens? That bus voltage will become 0. That bus voltage will become 0. So that V2 will become 0. 0. The post fault voltage. Now, if you calculate the pre-fault current, I is equivalent to V1 at an angle of delta minus V2 at an angle of 0 divided by the line impedance is Z line. Z line. Now, in this equation, the second bus voltage has become 0, so that this will be V1 at an angle of delta divided by Z line. Z line. And we know the transmission line impedance is very small and the supply voltage is very large. So a large value divided by very small value, therefore the current in the system will be very large. The current in the system will be very large. Therefore, we can say the second consequence of the short circuit will be what we can say this one? High current. So we will get high current. That's what I have given here. That is the low voltage and high current. Low voltage and under voltage and over currents. Clear? And next one, if you see here. Right. Please check here, students. Whenever the voltage of one bus has been reduced, we know from the decoupled equation, the active power always depends upon delta, the reactive power always depends upon the voltage. So if you see all those equations, the active power P is always proportional to change in delta, and the reactive power is always proportional to change in the voltage. If you check here, the active power P is proportional to delta 1 minus delta 2, and the reactive power Q is proportional to magnitude of V2 or V1 minus V2. V1 minus V2. That is the reactive power value in the system. Clear? Now, in this case, we have delta 2 is equivalent to 0 and delta 1 is delta. And magnitude of V1 and magnitude of V2 has been given. And as the negative component V2 has been 0, the reactive power in the system is proportional to only V1. Therefore, more the V1 value, more will be the reactive power supplied by the source. As the source is supplying very huge amount of reactive power to the load will become highly lagging load. For example, so that if you see here, the current in the system is V1 at an angle of delta divided by Z line. And this Z line is approximately equivalent to J times of X line. So why? Because the resistance of the line will be very small and we can neglect that. The resistance of the line is approximately equivalent to 0. Now substitute that value. Therefore, what we will be having here? The current in the system I is equivalent to V1 divided by V1 at an angle of delta divided by J times of X line. And what is the value of J, students? The value of J is nothing but 1 at an angle of 90 degrees. So the operator J always rotates the vector anti-clockwise by 90 degrees. Therefore, we can write here, it will be V1 at an angle of delta divided by X line at an angle of 90. So therefore, it will be V1 divided by X line at an angle of delta minus 90. So for more stability of the system, the value of delta will be very small. That means the difference between delta 1 and delta 2 will be very small in the system. Therefore, we can take this as V1 divided by X line at an angle of minus 90, nearly. Therefore, we can say the current in the system always lags the voltage, nearly to 90 degrees. Nearly to 90 degrees. Therefore, the system is becoming highly lagging system under the short circuited fault condition. Therefore, we can write here. Therefore, we can write here. The system will become highly lagging in nature. Therefore, the current I lags V by nearly 90 degrees. Nearly 90 degrees. And power factor will be highly lagging. Highly lagging. So that we can say very low power factor operation. Low power factor operation. So why we are getting low power factor? As the reactive power supplied by the source is directly proportional to V1 only. As more the value of V1, the source has to supply huge amount of reactive power to the load. So that high reactive power flow from source to load. Which means that the source is supplying a huge amount of reactive power to the load. There will be more burden on the source. Therefore, whatever the amount of apparent power you are having, most of amount of apparent power is converting into the reactive power, and very less amount of active power only we are delivering. For example, students, if you check here, whenever if you are having a generator of 500 kVA, for example, 500 kVA, and it is seeing a load of, it is connected to a load of, suppose for example, unity power factor. So in this case, if you check here, the apparent power is 500 kVA and the power factor is cos phi is equivalent to 1. What is cos phi, students? The value of cos phi is equivalent to P by S. As cos phi is 1, so the active power P value is exactly equivalent to S. So which is nothing but 500 kilowatts. Therefore, this is the apparent power value and this is the active power value. The total active power or the total apparent power is converting into the active power, and there is no reactive power value supplied by the source. Source is not at all supplying any amount of reactive power. Why? Because the load is not at all taking anything. Clear? Now coming to the next one. For example, if the same source of 500 kVA is seeing a load of some 0.8 power factor lagging. Clear? In this case, if you check here, S will be 500 kVA and cos phi, which is nothing but P by S, which is nothing but 0.8. So that 80% of 500, what is 80% of 500? So 400. Therefore, the value of P is nothing but 400 kilowatt. So that we are not able to deliver total amount of apparent power as active power. So active power delivered value will be reduced. Therefore, what happens to the value of Q? Q is nothing but P into tan phi, where P is 400 into tan phi. So tan of cos inverse of 0.8 will be 0.75. So that it will be 300 kVA. Therefore, we are unable to deliver total amount of apparent power as active power. So that has been divided into the vector sum of active power and reactive power. So that here S is equivalent to P plus JQ and S square is equivalent to, so P square plus Q square. Like that we can calculate. So in this case, the value of Q has been 0 for unity power factor load, and in this case, the value of Q is not equivalent to 0. For example, when the load is 0 power factor load, suppose, please check here, if the load is ZPF load, the same source is seeing a load of 0 power factor lag. So the rating here it is 500 kVA. 500 kVA. Under this case, what happens? If you check here, current power is 500 kVA. Yes, and cos phi is 0. When cos phi is 0, the active power P will become 0, so that we are unable to deliver any amount of active power to the load. We are completely delivering reactive power. Q is 500 kVAR. So that we are unable to deliver any amount of active power. When we are not delivering any amount of active power, what is the use of that load? Clear? So that for low power factor load of the system, we are delivering very less amount of active power. That is the problem. So that is the next consequence. So low power factor operation. And we know we are getting the unbalanced operation. Why we are getting the unbalanced operation? Under no load condition also, the system is having some currents. So IA we are having, so sometimes IB we are having, sometimes IC also we are having sometimes. Clear? That is the unbalanced operation of the system. So for LG fault, IA will not become 0. For LL fault, sometimes IB and IC are existing. For LLG fault, sometimes we are having IB and IC along with, they are flowing there. And in three-phase fault, we are calling that as balanced operation. Three-phase faults. Clear? And so whenever we are having huge amount of current flow, there will be, please check here, when the current in the system is increasing, whenever the current in the system is increasing, so we are saying that the loading on the system will be highly increasing. So because of that one, so which means that the load means the short circuit is taking huge amount of current from the system. So because of that one, the synchronous difference, speed difference between the stator magnetic field and the rotor has been increased, and because of that one, the rotor speed will be increased. So that whenever the rotor speed is increasing, we are getting high frequency operation, right? So because of high currents, so the frequency of the system or the speed of the system will be increasing. The speed is going to increase, and because of that one, the frequency is going to be increased. So that we are getting the high frequency operation of the system, right? Sometimes we are getting low frequency also, right? So according to the equal area criteria analysis, we are going to get the high frequency operation for the synchronous generator, and because of the high currents, we are getting the low frequency operation also. Both we can get. So in equal area criteria analysis, we are going to get high frequency operation for generator, low frequency operation for the synchronous motor. Both we can get there, right? High frequency for generator and low frequency for motor. So both we can get there. And the unstable operation. So the unstable operation means whenever the frequency is changing, the stability of the system will be reduced. So because of this high frequency operation, so because of that high frequency operation, the stability of the system will be reduced. Clear everybody? So that the stability of the system will be continuously reducing because of the unbalanced frequencies and unbalanced speeds. See here, the rotor speed of the generator is not is equivalent to the synchronous speed whenever the speeds are changing. So that the synchronous generator or synchronous motor, they are coming out of the synchronism. And because of that one, the stability of the system will be reduced, right?
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least.
Yeah, so that's all for today's session, students. So I think you got some new points, some extra points here. And we can expect at least one or two questions in this fault analysis every year. And that's all for today's session. We'll meet in the next class, right? Thank you.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2021. I have been associated with ACE Engineering. I have taken various programs like Life's main classes, Postal Study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself, Abhishek Kumar Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now, I divide my preparation strategy into three basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESC 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESC 2020 and ESC 2021.
Hello everyone, my name is Karthikeya Kaushik and I